Hi everyone. In this video, I'm going to be talking about binary number systems, and you'll see why this is relevant in a future video. It's necessary for one proof about cardinalities of sets. But basically, binary refers to number systems which don't use 10 as a base, but instead use 2. So what exactly does this mean? So we typically use base 10, and base 10 means that we have 10 digits available to us per place in our numbers. So for example, if you look at the number 231, this has 3 places. And there are 10 choices for how we use any place. We could use 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9 in a single place. Those are the digits available to us. And that's what it means to be base 10, essentially. And it also means that each position in our numbers refers to the number of a certain exponent for 10. So in this case, 1 really represents 1, 3 really represents 30, and 2 really represents 200. And this means that this is 10 to the 0 power, this is 10 to the first power, and this is 10 to the second power. Because 10 to the 0 is 1, so 1 times 1 is 1, so that's all this represents. 10 to the first power is 10, so that's 10. 3 times 10 is 30, so that's what this represents. 10 squared is 100, 2 times 100 is 200, and that's what this represents. And you can extrapolate this to a thousands place, 10,000s place, and so on. But we can also write our numbers in different ways, and this is unintuitive the first time you see them. But in base 2, that means you only have 2 options for your digits in your numbers in any given place, and each of the places represents a different power of 2. So for example, so first of all, the fact that you only have 2 digits available to you means that you can't use 2, 3, 4, 5, 6, 7, 8, or 9. You can only use 0 or 1 in a given place. So now what might a number look like in binary? So we can look at one number, maybe 1, 0, 1, 1. So there are 4 places here. And so again, you represent them with different powers of 2, starting with 2 to the 0, 2 to the 1, 2 squared, and 2 cubed. So now what does this number represent in base 10, which is more familiar? So this is 1 times 2 to the 0, 2 to the 0 equals 1, 1 times 1 equals 1. 2 to the first power is 2, 1 times 2 equals 2, so this represents 2. And you're adding all of these, by the way, because they're representing kind of separate things. 2 squared is 4, but you have 0 of them, so you get nothing out of that. And then 2 cubed is 8, times 1 is 8. So 8 plus 0 plus 2 plus 1 equals 11. And so 1, 0, 1, 1 in binary is equal to 11 in base 10. Base 10 is also called the decimal number system. Yeah, so that's the other thing that's important to note is that you can represent any number that you can represent in base 10, you can also represent it with base 2 in binary. So the reason for this is kind of that for any number of decimal places, you can get within 1 of using 1 additional decimal place. So to give you a concrete example, just suppose you have 3 decimal places and you're in a binary number system, you can think about what the largest number is you can represent. So that means you want to use the highest possible digit in every decimal place, not every decimal place, in every number place. And the highest digit in binary, there's only 0 or 1 are your only options, so it would be 1 in every position. So in 3 digits, you can represent 2 to the 0, 2 to the 1, 2 to 2 squared, which is 4 plus 2 plus 1, which is 7. And if you want to represent the next number, you can. There are no gaps between the options you have with 3 decimal places, 3 digits and 4 digits. So the smallest number you can represent with 4 digits is going to be the largest number you can represent with 3 digits plus 1. So you can see this, the smallest one with 4 digits. You wouldn't need to use 4 digits if the first was anything other than a 1. If it was a 0, you could just ignore that. So it has to be a 1 here, but then you can put zeros everywhere else, and it's valid for 4-digit number in base 2. And in this case, it would be 2 cubed plus nothing, which is just 8. So you can see that's 7 and then 8. So this is just saying that you can get any natural number using binary, because in general, and this doesn't just apply to this case of 3 to 4 digits, in general, I can write explicitly what the statement here is. It's that the sum from n equals 0 to k of 2 to the nth power equals 2 to the k plus 1 minus 1. And so again, this is in the case that we were just looking at, that was k equals 3. So that was 2 to the 0. Actually, k equals 2. It was 2 to the 0 plus 2 to the 1 plus 2 squared equals 2 cubed minus 1. But you can do this on and on. You could probably prove this by induction, which I should have proved by induction previously. You can try and follow that process. I don't think I'll prove it in this video, just for the sake of time. But you can pretty intuitively start seeing that this is true. You can represent any number in binary, and there are no gaps between numbers. One last point that's worth making which is useful in our proof that's coming up in a future video, is that this isn't only possible for natural numbers. I've shown you numbers like 1, 2, and so on, 7 and 8, 11, but you can also do this for numbers smaller than 1, and things that aren't natural numbers or whole numbers or even integers. And essentially, we've been looking at 2 to the 0 as the last decimal place and then going up from there. But we can put a decimal point and then continue and use negative decimal places, 2 to the minus 2. And this is essentially what we're doing in base 10, so I can start there again, which is more natural. You can look at hundreds place, a tens place, a ones place, and then your tenths place, which is 10 to the minus 1, your hundredths place, which is 10 to the minus 2. And so you can represent any decimal that you can, decimal that you can write like this. You can also write in binary with numbers after a decimal point. Maybe it should be called a binary point in that case. But yeah, so you can, for example, write 0.5 as just zeros over here, and a 1 and a 0 here, because that's 2 to the minus 1 is 1/2, so you get 1 times 1/2, so that's just 1/2. And then you can also get basically more precise with your decimals as you use more and more places, because it works essentially the same way as with decimals. And you can continue to use more and more places to get more and more precise. And you can represent any real number in binary as well, if you use infinite decimal places, infinite places after the point, just like you could with the typical base 10 number system. So yeah, again, as I said, this will be useful for a future proof regarding cardinalities, which should actually be my next video. Thanks for watching.